everyone. In this video, you're going to learn about parametric equations. So before we got to parametric equations, so like in our pre-calculus studies, whenever we would graph a function, let's say it's y equals f of x, and the graph was a curve, we would refer to the graph as a plane curve. Plane meaning geometric plane, not plane meaning simple. But anyway, because we were graphing the function on a coordinate plane and the graph is a curve, we might call it a plane curve. All right, now when the equation involved two variables, x and y, it was possible to know where an object is located or has been. However, we might need to know when an object is at a given location, x comma y. So parametric equations just introduce a third variable, t, which is called a parameter, so that we can write both x and y as functions of time. And if we do that, we obtain parametric equations. So parametric equations are just where x and y are now both functions in terms of time. So we're just introducing a third variable called the parameter, okay, which is often t for time. Okay, so parametrically defined functions. If the x and y coordinates of a point on a graph are given as functions f and g of a third variable, usually t, then we would write x equals f of t and y equals g of t, and we would call these parametric equations. And again, we would call t the parameter. So when t represents time, as it often does, then we can view the curve as a graph of a moving particle as time varies. Okay, now note that the curve C consists of all the points where C of t equals f of t, comma, g of t. Okay, sometimes you'll also see this as C of t equals x of t, comma, y of t. Okay, again, just bringing in that x and y are both functions of time. And so we would refer to the graph, the curve, as a parametrized curve. And the parametric equations are a parametrization for C. Okay, now that you understand a little bit more about parametric equations and that it's just now two equations, both in terms of t, how do we graph parametric equations? Well, we graph using a table of values, but we're going to set up our table a little bit differently. When we set up our table, we need to have a column for t for time. We need to have a column for x, which equals t squared. And we need to have a column for y, which equals t cubed minus 3t. And then we're just going to plug in some values for t, so I'm just going to keep it simple, 0, 1, 2. And we're going to plug into both equations, and then that's going to give us an ordered pair to plot on the coordinate plane. Okay, so if I plug in 0 for t, 0 squared is 0. And if I plug in 0 into y, we get 0 cubed minus 3 times 0, and all that is still 0. So you're just going to plot the point at 0, 0. Okay, if I plug in a 1, 1 squared is 1, 1 cubed is 1, minus 3 times 1, so that would be negative 2, because we end up with 1 minus 3. Okay, so 1 negative 2 is here. And then if I plug in a 2, 2 squared is 4. Okay, if I plug in a 2, 2 cubed is 8, minus 3 times 2, so 8 minus 6 is 2, and so then I'll plot the 4, 2. Okay, so then we're going to connect the points to the curve. Now, to show the orientation on the curve, or to bring time into this, like how do we represent time in this graph? One way to do that is to use arrows, so we can kind of show the path that was taken as we plotted the points. Or sometimes you will also see where Time is just written next to each point. So this point was when t equals 0, this point is when t equals 1, and then this point is where t equals 2. Okay, so that is how we graph parametric equations. All right, the next thing that you want to be able to do is remove the parameter. So by removing or eliminating the parameter, we are rewriting the parametric equations as a function that we're used to, y as a function of x. Okay, so we're just going to remove the parameter and we want to have an equation y in terms of x. So how do we do that? Well, you take the equation that x equals and you solve it for t, and then we're just going to use substitution in our other equation. Okay, so if I were to solve for t, I think to get rid of that square root, I would just go ahead and square both sides, which will give me x squared equals 1 over t plus 1. And then I would multiply by t plus 1 on both sides, but then I'd have to turn around and divide by x squared. So we'd end up with t plus 1 equals 1 over x squared. And then I could just subtract the 1 on both sides to get t by itself. And then if I found a common denominator, like converted the 1 to x squared over x squared, I'd end up with 1 minus x squared all over x squared. Okay, so now we're just going to substitute that in our other equation in place of t. So we'll have y equals 1 minus x squared over x squared all over 1 minus x squared over x squared plus 1. So you can see where I just replaced t with the 1 minus x squared over x squared. Okay, then to simplify this, I'd start in the denominator. To add the fractions, we need a common denominator, so I can convert the 1 to x squared over x squared. When I add my numerator, the 1 minus x squared plus x squared, that's all just going to equal 1. So this is what I'm going to have now. And then I multiply by the reciprocal. So I flip the bottom fraction, the x squareds will cross reduce, and we'll get y equals 1 minus x squared. Okay, so that's easy to graph. We'll go back to our parent function, which is x squared, which is a parabola. This one is flipped over the x-axis and shifted up 1. And I could also write this as negative x squared plus 1. So basically, it's just a parabola that opens down and is shifted up 1. Okay, now I wanted to show you that we can also use trigonometry to eliminate the parameter. So in order to do that, we're going to use one of our trig identities. This is called the Pythagorean identity. Hopefully it looks familiar. Sine squared of theta plus cosine squared of theta equals 1. So we're essentially going to, in order to use this identity, notice how x equals 4 times cosine theta. I'm going to actually get cosine theta by itself, so I would divide by 4 on both sides. So that'll give me x over 4 equals cosine theta. And then because I want the cosine to be squared, so I can use the Pythagorean identity, I'm just going to square both sides. So then I'll have x squared over 16 equals cosine squared of theta. Okay, now I'm going to do the same thing with y. So we have y equals 3 times sine theta. I'm going to divide by 3 to get sine theta by itself. And then I'll square both sides. So we'll have y squared over 9 equals sine squared. And then I'm just going to plug in to this Pythagorean identity, which I can also write as cosine squared plus sine squared. So if I plug into that and replace the cosine squared with x squared over 16, I'll get x squared over 16 plus, replace the sine squared with y squared over 9, and then this all equal 1. I know this probably does not look that familiar, but this is actually the equation of an ellipse, which is what's called a conic section. So to graph the ellipse, so basically because the x squared is over 16, if I square root the 16, I'll end up with a point at 4 and -4 on the x-axis. And then because the 9 is under the y squared, if I square root the 9, I end up with +3 and -3 along the y-axis. And then basically, if you just connect the points, your ellipse looks like this. So this is the graph of an ellipse. Okay, but anyway, the main thing I wanted to show you there is that we can use trigonometry and the Pythagorean identity to eliminate the parameter, and we ended up with the equation of an ellipse. So some other scenarios, you might end up with the equation of a circle, possibly. Okay, now, when you are interested in the position, direction, and speed at a given time, you need to parametrize the curve of a rectangular equation. Okay, so this is kind of like going the other way. So we looked at a couple examples where we removed the parameter. This is where you're going to start out with an equation, y in terms of x, and we want to turn it into a set of parametric equations. So the easiest way to do this is to let x equal t, and then just represent y as a function of time. Okay, so one way that I could parametrize the curve of this rectangular equation is I'll just let x equal t, which means in that case y would equal 2 minus t squared. And so I just parametrized, and that's a really hard word to say, the equation y equals 2 minus x squared, meaning I just turned it into two parametric equations. So, all right, you guys, so those are the main things you want to be able to do when dealing with parametric equations. This is like the pre-calculus of parametric equations. In the next video, we'll get into some calculus with the parametric equations, but I just wanted to give you a little bit of practice just dealing with them, understanding what they are, knowing how to graph, knowing how to remove the parameter, and then also how to turn a rectangular equation into parametric equations. All right, you guys. Well, as always, thank you for watching, and have a good night.